Hi, this is a quick video to review the review that we did to get back to our square roots. This is going to go kind of quickly, so go back to your notes where you had lots of links to websites that showed you how these worked. So if you're simplifying a radical, there's two approaches some people use. One is to come up with the biggest possible perfect square factors that 72 can be broken into. And so if you know your perfect squares well, 36 is the largest perfect square factor of 72, so I can break this into two radicals whose radicands multiply back together to be 72. I know the square root of 36 is a whole number. The square root of 2 has no more perfect square factors, so I would be done. Now, there's another camp, the camp that breaks it down into its prime factorization. So what they do is they take 72 and they first split it apart into any factors that come to mind, 8 and 9, for instance. And then they break those down until they get to prime factors. And you've done prime factorizations before, so I always circle when I get to a prime. That way I know I'm done breaking a number down. Okay, so 72's prime factorization is the multiplication of 3 sets of 2 and 2 sets of 3. What we know about square roots is that any two factors multiplied together create a perfect square, so those two would create a factor of 9, whose square root would be a 3, and the symbol's removed because I've already taken the square root. Then this doubled set here creates a square root that comes out to be 2, and then that single factor of 2 that has to stay underneath because it's not a perfect square factor. And we can also get to the simplified form of 6 square roots of 2. The most common thing I see students doing, however, is getting one perfect square factor out and then not really checking or recognizing that they get this far and they think they're done because they have done some radical simplifying. However, they haven't taken out the largest or all the perfect square factors, so 8 cannot stay and be called simplified, so you'd have to keep going. So it isn't that you have to get the largest perfect square factor out first, but you have to recognize then when you have to continue simplifying your radical expression so that the final expression from any one of these methods does not contain a radical whose radicand has a perfect square factor other than 1. Fractions. So this always comes up, and there's no perfect way to teach you every possibility of fractions that comes up. You have to get the hang of kind of how multiplication and division with radicals works. So if the entire fraction's under the radical, like the top two, I've got two possibilities here. If I could go ahead and take the square root of the top and the bottom right away, but I would urge you to first check to see if the fraction can be reduced. We cannot leave a radical in the denominator, so we want to plan ahead a little bit. On the second radical expression I see, if I were to simplify 21/27 first, not take its square root value, but simplify it, that leads me to something that when I take the square root of both the numerator and the denominator, will lead me to something that does not leave a radical in the denominator right off the bat. So I'm not going to have to do any, trying to erase that. Not going to have to do any extra simplifying here. Square root of 7 does not have perfect square factors, and 3 comes out that way. So if I do a little advanced work, maybe I can leave out having to do a lot of work with things like multiplying by the square root of 27, which I'd prefer not to do. However, in the first example, we can't do that. 3/8 is as simplified as it gets. So what often happens is when we go to take the square root of both parts, then we realize that we have a radical in the denominator and we're not allowed to leave it. So what needs to happen is a rationalization, a multiplying by some square root over square root. You can always use the one that is currently the denominator because that fraction that I just wrote with the square root of 8 over the square root of 8 is really worth 1. So when I go ahead and I do this, I will have the square root of 3 times the square root of 8 multiplies back together. And in the denominator, I get the square root of 64, which some of you recognize right away that that's 8. My last step then would be to make sure that my radical in the numerator also is simplified, and we can see that it's not. So I'm going to break the square root of 24 into its perfect square factor. So I have 2 square roots of 6 over 8. and you guys asked for the multi-step ones, not the really short, easy ones, then that 2/8 needs to be broken down. So I have square root of 6 over 4, or 1 square root of 6 over 4. Now the two that are left, we also want to think about, and of course there's going to be an announcement to come over and interrupt my video. So the 10 over the square root of 2, so we can't get rid of that square root of 2 in the denominator any other way than this rationalizing process. So I'm multiplying, and it's not just multiplying by the square root of 2, it's multiplying by that fraction that's really worth 1. So when you multiply a whole number and a radical, they sit next to each other. When you multiply two radicals, that goes to the square root of 4, which is 2. Then that 10 halves needs to get simplified, so we're at 5 root 2. And the final one, the 8 square roots of 12 divided by 6 square roots of 3, I can always put two radicals back under one radical sign if they're dividing, just as I can when they're multiplying. So 8/6 right away, I'm going to reduce to 4/3. But then that square root of 12 over square root of 3, if I want to think about it, that can go back under one radical since they're both square roots. Then that's really taking the square root of 4, which is 2. So I get 8/3. So I want to be flexible with my calculations and not say, but I thought we always do this. We've got to have a couple techniques we can use when we multiply and divide. Adding and subtracting, however, are totally different. As with fractions, fractions can only add if they have like denominators. Now, when you see two fractions, if they don't have like denominators, you work to get them to. When I see two radicals to add or subtract and they don't have a common radical, then I need to see if simplifying them will help. So I'm going to simplify square root of 200, and if you need to see how to do that, go back to the beginning or to some of your other videos. That's 10 root 2. And then I'm going to simplify my 6 root 18, and root 18 is going to give me 3 root 2. So when I simplify my two radical expressions, I have 10 square roots of 2 minus 18 square roots of 2. These are now like terms. Like terms can add and subtract. The radicals do not change because you're saying 10 of something, take away 18 of the same kind of item. If that was 10 square roots of 2 minus 18 square roots of 7, then I'd have to leave those two terms as they're not like terms, and they would both appear in my answer then. Multiplying two radicals, the last thing we'll do on here, as long as this is all one expression with a multiply in between, and this is all one expression, then I'm not distributing because it's only a one term times a one term. But since it's all multiplying, I can think of the commutative property you learned in algebra about how multiplication, when it's the only operation, can be reordered. I can reorder the first two so I can multiply and get 20. And then I could take these two radicals, and when they're broken up and they don't produce a square root factor, then I can multiply them back together.